So hi folks, welcome back to the channel. We will have this amazing total solar eclipse that will occur on April 8th in the USA and in Canada. So the entire morning I have been testing out different kinds of photography gear to capture the sun. So you can see here, this is a DSLR camera with a telezoom lens and a solar filter. And here we have two smart telescopes, the Dwarf II and the Seestar S50. And in this video I will share my experiences and some of the pros and cons in using each of these photography setups to capture the sun. I hope you like it, and let's go! The total solar eclipse will be visible in parts of Mexico, the United States and Canada on April 8th. To visit the full eclipse, make sure you position yourself within the path of totality. For detailed information, check out timeanddate.com. Once you're in the path of totality, you'll experience a breathtaking event. The moon will gracefully advance in front of the sun. This will take about 75 minutes and lead to a climax where the moon completely obscures the sun. At this point, the sun's corona will be on full display, allowing you to safely remove your solar eclipse glasses or filters for an immersive experience. You may see some bright stars and even a bright comet which will be close to the sun on April 8th. After a few minutes, the moon gradually moves away from the sun until the full disk of the sun is restored. The entire celestial event spans about 3 hours and it will be an unforgettable show. You have various options to capture the total solar eclipse. You may want to record a seamless time-lapse video to document the entire event. Alternatively, you might opt to capture some high-quality photos or videos of the sun during the different phases of the eclipse. And then there are these precious few minutes at totality where you want to take off your solar filter to capture the sun's corona, the stars, or perhaps even a comet in the daytime sky. In this first test, I used my 100 to 400mm Tamron telephoto lens and an affordable tripod to capture the sun on a windy day. I placed a Baader solar filter in front of the lens cap to safely capture the sun. I used a remote camera app on my smartphone to take pictures, which avoids serious vibrations when pushing the shutter button manually at a high focal length, as this leads to blurry pictures. A remote shutter cable can also do the job for you, but I didn't have a shutter release output on my Canon M50. You may want to take plenty of batteries with you, as you don't want to run out of power during the event, which lasts for about 3 hours. Links to the camera, the telephoto lens, the app and the solar filter can be found in the video description below. This is the live view of the camera app I used that day, so you can follow along with my DSLR test. The app displays the shutter speed and f-ratio on the bottom left and the ISO level at the bottom right. As a first step, I pointed my camera at the sun and moved the telephoto lens to 400mm. I set my camera dial to M and put my focus to manual, as the autofocus option is often unstable when focusing on a bright object like the sun. I found that a shutter speed of 1/200th of a second at the lowest ISO setting of 100 with an f-ratio of 6.3 revealed the sun's disk. To focus the camera, I dropped the shutter speed to 1/800th, which revealed some sunspots on the sun that day. The sun is at its solar maximum in 2024, so it is very likely you will be able to see some sunspots during the eclipse on April 8th as well. Next, I used the magnifying glass, which is available on most DSLR cameras when in manual focus mode, to do a 10x digital zoom on the sun's disk, and I tried to focus on the sunspots. This was super challenging, as manually focusing the camera at 400mm focal length leads to considerable shake, as you can see in this live view. After I was satisfied with the focus, I started taking some test shots. Alright, let's do some math and consider creating a time-lapse video of the full event. If you take pictures at 2-second intervals, you'll end up with 30 photos per minute. If we take a video speed of 30 frames per second, every minute will be 1 second in your time-lapse video. The total solar eclipse will last for about 3 hours, which includes the moon slowly moving in front of the sun, the total eclipse, and the moon slowly leaving the sun's disk again. Let's say this lasts for about 3 hours or 180 minutes, so your time-lapse video will last for 180 seconds or about 3 minutes. So let's discuss the main issue when using a regular tripod to create such a time-lapse video. I programmed the app to shoot 250 photos at 1 second intervals. As you can see, the sun slowly moves out of the field of view of the camera. So with a tripod, you need to reposition your camera approximately every 5 minutes to keep the sun centered. If that's your strategy, I'd recommend you practice how to manually track the sun before the event so you don't run into any kind of last-minute surprises. A second issue, as mentioned, were the strong wind gusts that day. I put 250 pictures in a movie sequence and I ended up with this shaky 5-minute time-lapse video. The good news is that we have lots of processing software available nowadays, so I aligned the photos and created this more stable video of that same 5-minute time-lapse. It is also wise to consider your photo format. RAW photos will give you the best processing options, but they are quite sizable and they do take more time to process in high volumes. High quality JPEG files are less sizable and easier to process in volume, but they provide you with less options to manipulate the pictures. Still, JPEG may be a viable option to create a continuous time-lapse video, considering that the details of the sun are limited to a couple of sunspots at 400mm focal length. Now let's consider the few moments you have to image the total solar eclipse. At this point in time, the moon fully covers the sun's disk and the faint corona of the sun should be visible for only a couple of minutes. At that time, you want to take off your solar filter and decrease your shutter speed to capture the corona of the sun. As I didn't have a solar eclipse during that day, I simply decreased the shutter speed of my DSLR with the solar filter still on, and I found that a 1/15th of a second shutter speed was pretty good as it revealed some halos around the sun. This corresponds with a fact sheet of Fred Espinac indicating that at ISO 100 at around f6.3 you should get a decent picture of the corona of the sun at 1 solar radii when using a shutter speed of about 1/15th to 1/8th of a second. You can find a link to my blog with a full overview of recommended ISO levels, f numbers and shutter speeds during the total solar eclipse in the video description. Here are some high quality raw pictures of the halo around the sun I managed to capture that day. Here's a simulation of how the solar eclipse may look like when using a DSLR camera and a 400mm telephoto lens. I created a moving black circle to simulate the moon getting in front of the sun, and I used the photos I took with my DSLR that day to create this time-lapse video. So what about using smart telescopes? Well, let me show you my test with the Seestar S50 Smart Telescope during that same windy day. It is super easy to engage in solar imaging using a Seestar S50. You can find a full review of the Seestar S50 in the video description below and on my website astroforumspace.com. You can switch on the Seestar S50 Smart Telescope and connect to the telescope over Wi-Fi using the Seestar app. In the main screen of the app you'll find a solar mode option. By selecting that mode, the app will ask you to place the solar filter that comes with the Seestar S50 in front of the telescope lens. You can use the up and down arrows in the app to move the telescope. Now, just put the solar filter in front of the telescope lens like this and make sure your tripod is level and the Seestar is facing the sun. After that, just hit installed and the Seestar will automatically find the sun in the daytime sky. The full disk of the sun nicely fits the field of view of the Seestar S50, and that is no coincidence. You can fit the automatic tracking button on the top right to center the sun in your field of view. A great advantage with smart telescopes like the Seestar S50 is that it will automatically track the sun without having to reposition the telescope. The autofocus function is also pretty straightforward. Just press the AF function and place the green rectangle at some sunspots and the telescope will autofocus within seconds. People have expressed concern about heat buildup when using the Seestar on the sun for multiple hours. I had the Seestar pointed at the sun for over 2 hours during this test and it didn't show any issues. Let's move on to capturing options. The easiest way to capture the sun is to select the photo mode at the bottom of your screen and just press record. Seestar will take a JPEG picture of the sun and store that picture on its 64GB memory card and on your smart device. Here's an example of a picture of the sun. You can also use time-lapse mode to create a time-lapse video. When selecting the time-lapse mode at the bottom of the screen, the Seestar app will show you interval options ranging from 1 to 60 seconds. I decided to track the sun for about 10 minutes at 2-second intervals. After pressing the stop button, the Seestar saves the time-lapse videos in MP4 format on its memory card. Unfortunately, the tracking of the Seestar S50 is good, but it is not perfect. Here's that 10-minute time-lapse video played in just 10 seconds. The sun shifts around quite a bit. I use some processing techniques to align the disk of the sun across all the frames of the video, and here's what that 10-minute time-lapse video looks like after centering the sun, which is pretty decent. The 10-minute time-lapse video takes up only 15 megabytes of space, so you can easily time-lapse the whole eclipse, which will last for about 3 hours, which would create a 270 megabyte MP4 video file. A third option when using the Seestar S50 is taking videos. I selected the video mode in the bottom of the screen and I took a 5-minute video of the sun by pressing record. The Seestar captures video in MP4 format, which are saved to the memory card of the Seestar S50. You can easily transfer all videos and photos using a USB-C cable from the Seestar to your computer. The 5-minute MP4 file was about 75 megabytes in size, so that's about 15 megabytes for 1 minute of video. If you want to record the total eclipse across 3 hours, it would take 2.7 gigabytes of data, which easily fits on the 64 gigabyte memory card. There is also an option to save videos in RAW format. This format is made for nerdy astrophotographers like me who want to stack and process high-resolution frames of the sun to create a detailed, sharp picture. Using RAW, you can record up to a maximum of 10 minutes and each video will take about 1.4 gigabytes of space. You need to be familiar with various processing techniques such as debayering, stacking and sharpening software to create a high-resolution, sharp final picture. Going into details on how to do that will take too long in this video, but here's an example of a processed picture of the sun I created using a 2-minute RAW video that day. If you're willing to invest in learning how to process these raw videos, or perhaps you already know how to do that, you could opt to take a couple of raw videos during different phases of the eclipse and then process these images to create a series of high-quality processed pictures of the solar eclipse during its different phases. You can find more info on how to process such data on my website astroforumspace.com. During the total solar eclipse, which will only last for a couple of minutes, you want to take off the solar filter of the Seestar S50 to take photos or videos. There are a couple of things that make this challenging. The solar filter of the Seestar S50 is very much fixed in front of the telescope lens and you need to exert quite some force to pull it off. By doing so, you run the risk of moving the telescope. You may want to practice taking off the solar filter inside your house or create an alternative do-it-yourself solar filter, which is easier to remove from the Seestar. I left the solar filter on the Seestar during this test day and played around with the exposure settings. I increased the exposure setting by pressing the plus-minus icon and I increased it to 100. This was the resulting view. Whether this is enough to expose some of the corona, I'm not sure about that, but I could see some halo around the sun. There is also an option to switch to alternative capturing modes like scenery mode or lunar mode. This is a bit risky as the total eclipse only lasts for a couple of minutes and you will probably lose solar tracking when switching to other imaging modes. Here's a simulation of what the eclipse might look like with the Seestar S50, where I created an artificially moving black circle across the time-lapses and the videos taken with the Seestar S50 that day. Let's move on to the Dwarf II test. The Dwarf II is an affordable device with a wide field and a telephoto lens in one. You can control the Dwarf II over Wi-Fi. Just download and install the Dwarf Lab app, put the Dwarf II on a tripod, level the tripod, switch the Dwarf II on and connect to it using the Dwarf Lab app. For more info, you'll find some links in the video description below. You can buy an extra battery at extra cost, which can easily be switched. You can buy 2 ND solar filters for the Dwarf II at extra cost. It is easy to install these solar filters. Just screw them on the magnetic holder and place that holder in front of the 2 lenses like this. It is also easy to take off these filters during the full solar eclipse, which is nice. In the Dwarf Lab app, you can press Photo, which shows you a nice live view of the wide field lens with a green rectangle showing the field of view of the telephoto lens. It is easy to find the sun with the Dwarf II. The initial view is the view of the wide field camera. You can change the position of the Dwarf II by using the arrow keys at the bottom left of the Dwarf Lab app, and you can control the speed of the Dwarf II using the speed dial on the right. The green rectangle represents the field of view of the telephoto lens. Just move the sun to the green rectangle and switch to the telephoto lens by clicking on the small screen on the top left. In the telephoto view, you can make some minor adjustments to put the sun in the center of the camera's view. You can press the settings button to control the shutter and gain level of the telephoto lens. I found that a shutter speed of around 1/60th to 100th at 0 gain revealed the sunspots that day. The Dwarf II manual suggests a shutter speed of around 1/200th of a second, so I'd recommend experimenting with this. You can pinch the screen to zoom in and use the focus icon on the right to focus on the sunspots. You can click Auto to autofocus, or you can use the plus and minus buttons to manually focus on the sun. The Dwarf II has a specific solar tracking function. Clicking on the function icon at the bottom right reveals object, sun and moon track options. Clicking on Sun Track shows a screen which warns you to always use the solar filters, level your mount and put a shutter speed to about 1/200th of a second at 0 gain. I just received a Dwarf Lab app update that morning and I updated the app. Unfortunately, after clicking yes, the Dwarf II moved away from the sun instead of tracking it, and it switched to Astro mode settings. This was very frustrating because solar mode used to work without any issue before. Restarting the telescope, restarting my phone and restarting the app didn't solve the issue. I sent a message to Dwarf II about this strange behavior, and this continues my love-hate relationship with the Dwarf II, as this kind of erratic behavior happened before. The best thing Dwarf Lab can do, in my opinion, is make their software more reliable, so these kind of things don't happen in the future. I hope you don't have this kind of erratic behavior, and that the Dwarf II will track the sun as mine did before the update. Anyhow, I decided to continue the test by putting the Dwarf II video mode, and I recorded a 2-minute non-tracked video of the sun, which looked like this. The video took about 440 megabytes of space, so the Dwarf II records at about 220 megabytes per minute. If you want to record the whole 3 hours, you would end up with a 40 gigabyte MP4 video file, which would just fit the 64 gigabyte SD card of the Dwarf II. It may be wiser to use the time-lapse mode instead. You can select time-lapse and hit the record button. The Dwarf II will start imaging the sun with an automated interval of 1 second and will continue to do so until you hit the stop button. You can adjust the interval and time-lapse duration if you want in the function settings on the bottom right. You can choose a time interval from 1 to 60 seconds. The Dwarf II saves time-lapse videos in MP4 format and replays them at 30 frames per second. So at a 1 second interval, a 3-hour time-lapse of the entire event would replay in about 6 minutes. A 2-second interval would replay in about 3 minutes, and so on. Using the time-lapse option, I recorded the sun for 7.5 minutes as the disk slowly moved beyond the field of view of the telephoto lens without the solar tracking working. The file was about 50 megabytes, so a 3-hour time-lapse at 1 second interval would take about 1.2 gigabytes, which would easily fit the 64 gigabyte SD card used by the Dwarf II to store the data. Here's that video, but with some processing applied to align the sun's disk across the individual frames. At totality, when the moon fully covers the sun's disk for a couple of minutes, it will be very easy to remove the solar filters from the Dwarf II. Just take the magnetic holder off the telescope and you're good to go. Also, The photo and video modes give you full control over shutter speed and gain. And you can even check out if removing the IR cut filter makes for some interesting photos and videos. The telephoto lens operates at f4.2, so a shutter speed of around 1/15 of a second or less should give you a nice view of the corona. The 100mm focal length telephoto lens will not provide you with the highest resolution pictures and videos, but if the solar track function works, it should be easy to operate the Dwarf II during the solar eclipse on April 8th. Here you can see a simulation of what the solar eclipse probably looks like with a Dwarf II telescope. So what kind of equipment are you planning to use to capture the total solar eclipse? Let me know in the comment section below. Or maybe you have some additional questions, I'll be happy to answer them. Also, like and subscribe to the channel if you found this video useful, and I do hope you have some clear skies to capture the wonderful total solar eclipse. See you in the next video.